Welcome to the Explainer. Every time you hear about some huge data breach or a nasty ransomware attack, there's this incredible digital detective story happening just behind the curtain. Today, we're going to pull that curtain back. We're diving into the world of malware analysis, how the experts take a piece of malicious code from being this silent, invisible threat and turn it into the very intelligence that keeps all of us safe. So, let's set the scene. Imagine your company's network. It's been breached. Sensitive data is flying out the door, the alarms are going off, and the only clue you've got is this totally cryptic name from your antivirus software. This right here, this is the exact moment a malware analyst gets the call. Their job is to take that weird, cryptic name and make it tell them everything. And that really is the million-dollar question. You're basically holding a digital bomb. You need to know how it's wired, what its target is, what it's designed to do, but you can't just let it blow up to find out. It's this incredibly delicate balancing act, this tightrope walk of investigation without causing an infection.
So how do they do it? Well, to solve this puzzle, analysts really have two main roads they can go down. You can think of it like a detective at a crime scene. You can either dust for prints and examine the evidence left behind, or you could watch a security camera recording of the whole thing as it happened.
Okay, so those two paths are called static and dynamic analysis. The first one, static analysis, is where you inspect the file itself. You're looking at its code, its structure, but you never, ever actually run it. It's exactly like studying the blueprints of a building. The second path is dynamic analysis. This is where you intentionally run the malware, but you do it in a super safe, controlled environment. You let it do its thing so you can watch what happens in real time. It's like putting a suspect in an interrogation room and just watching.
So let's start with that first path, the static approach. This is usually phase one of any investigation. It's all about gathering as many clues as you possibly can from the file itself without ever having to press the run button. An analyst will start by gathering all the surface-level stuff. They'll scan it with antivirus tools to see if it's a known bad guy. They'll calculate the file's hash, which is basically its unique digital fingerprint, to see if it matches any other known threats. And then they'll start digging for strings. These are just little bits of readable text inside the code, and they can be a goldmine, revealing things like IP addresses or file names. But if you find nothing, that's also a huge clue. It might mean the malware is packed. Think of it like a malicious program zipped up inside itself, waiting to unpack its real code only when it's running. It's a clever way to hide what it's really up to.
And this is a perfect example of what that looks like. On the right, you see the strings from a normal, healthy system process. But look at the one on the left, the suspicious one. It's full of references to weird registry keys and services that just have no business being there. Right away, that's a huge red flag, telling the analyst that this program is definitely not what it pretends to be.
But here's the thing. Sometimes just reading the blueprints isn't going to cut it, especially if the malware is really good at hiding its intentions. To get the real story, sometimes you just have to let the bad guy make a move. And that's where dynamic analysis comes into play.
Now, the absolute key to doing this safely is something called the sandbox. A sandbox is basically a virtual computer, a complete digital fake. It's totally isolated from the real network, from the analyst's machine, from everything. It's a digital quarantine cell where you can detonate the malware, and it thinks it's running on a real victim's computer, letting us watch its every single move without any risk.
And inside that sandbox, we're running some seriously powerful monitoring tools. What you're looking at here is from a tool called Process Monitor. Think of it like a super high-speed security camera, logging every single thing the malware does. We can see it here using regset_value to mess with the Windows registry. That's a classic move malware uses to make sure it runs every time the computer starts. And then we see it creating a new file with write file. Every action is captured.
Okay, but what happens when the malware tries to phone home, to connect to the internet? Well, we can't just let it do that. So instead, analysts use tools like INetSim to create a completely fake internet. This thing pretends to be all the normal web services, and it tricks the malware into revealing which command and control servers it's trying to talk to, all without ever alerting the attackers that we're onto them. Pretty clever, right?
But what happens when even that isn't enough? When the basic methods don't give you the whole picture? Well, sometimes, to find the really important secrets, analysts have to get out the digital scalpels and perform some much more intricate surgery.
I mean, what if the malware is smart? What if it uses really complex encryption to hide what it's saying? Or what if it's designed to detect when it's in a sandbox and just play dead?
For these really advanced threats, analysts have no choice but to go deeper, to peel back the layers of the code right down to its very core. And this is where we get into true reverse engineering. Using a special tool called the debugger, an analyst can literally step through the program's execution one single instruction at a time. They're reading the raw assembly language, the fundamental instructions that speak directly to the computer's processor. It's an incredibly painstaking and highly specialized skill, but sometimes it is the only way to uncover a program's deepest, most well-hidden secrets. So, after all this digital detective work, the blueprint reading, the sandboxing, the deep dive reverse engineering, what's the end goal? Why does all of this matter so much?
Well, the payoff is huge. It's all about turning knowledge into defense. First, the analyst gets a complete picture of what the malware can do. From that, they extract what we call indicators of compromise. These are the unique digital fingerprints the malware leaves behind, like specific IP addresses it contacts or file hashes. And then, those indicators are used to create detection signatures, which basically vaccinates our security tools against this exact threat. And this, right here, is the ultimate point. A single isolated malware sample, when you analyze it properly, generates the intelligence you need to protect an entire company network, or maybe even millions of computers all over the world. It completely flips the script from a reactive problem into a proactive defense for everyone.
At the end of the day, this is a constant cat-and-mouse game. Attackers are always coming up with new, clever ways to hide their tracks, and analysts are right there with them, inventing new ways to find them. And it's that tireless work, dissecting these threats one line of code at a time, that stands between a small contained incident and the next global cyber crisis.